Welcome back. In this video, we're going to discuss exactly how we get to the more general failure equations. That's the Goodman equation for fatigue failure, or the ASME elliptic. There's also a Gerber failure criterion. There's several different theoretical approaches to calculating whether or not a material will last 10 to the 6 or 10 to the 8 cycles. But we're going to look at how we get to those, and to do that we need to look at the more general case. So before we were talking about fully reversed stress, and fully reversed stress looks like this. Over time, the average value of the stress, the sigma mean, equals 0. And the sigma A, the amplitude, is equivalent to either the magnitude of the max, or which is of course equal to the magnitude of the minimum value of stress. So that's the most simple case that we could get, and when we were talking about that, we said, okay, fine, the fatigue factor of safety is the strength of the part compared to the stress that it's under. This is the fully reversed case. So we're going to get into a little bit more of the actual failure criterion and see how this needs to be modified for the fact that in most cases we actually have some residual stress going on. So recall one of the cases that we could have when we introduced this stress approach, the fatigue approach, is what was called fluctuating stress. So stress over time may fluctuate about some mean which is not 0. This sigma mean is absolutely not 0. And its amplitude goes between some min and max. So in general, it's always true that the mean is the average, so sigma max plus sigma min over 2. That's always true, and this is also always true, that the absolute value of the maximum minus the minimum over 2. And this can be done for shear as well. Just replace with tau max plus tau min over 2, or tau max minus tau min over 2. And that's how we come up with those, what we call the mean and the amplitude stress. So it becomes important when we look at this mean and amplitude stress for how a part fails. So consider for the fact that when we did the RR Moore test, we didn't actually do it, but when somebody did it, all of the stress that they were doing was amplitude stress, and they found out when it would break under a purely amplitude stress type of loading situation. Now, if that's not our situation, instead we have one of these where we've got the mean stress, then we need to figure out how it's going to break with that combination. Now, if you think about it, it's almost, if you have both a sigma A and a sigma mean, there is an infinite combination of those. So there's no way any experiment could be formed that would be able to test every combination of sigma A and sigma M and then put them in some sort of representation or a graph that you could read. So instead, we can plot logically, and this is where the Goodman equation comes from, by the way. We can plot the amount of amplitude stress that we can have, and we can plot the amount of mean stress that we can have. So if we consider a fully reversed case, that means the stress is sigma A, and all the stress is sigma A, and sigma M equals 0. That puts us on this axis, and there is some point where if the stress is high enough, it will yield. We'll call this the yield point. Also, and it will yield in the very first time it is attempted to use. Also at some point, there is the endurance strength, where if our stress is higher than this endurance strength, it will not last the million cycles. All right, so that's in the amplitude direction. Now let's go in the opposite direction. In order for it to break, we could get to, if we just have mean stress, if the amplitude is 0 and we're going along this line, we just have mean, well, that's the same thing as saying it's basically static loading. We just have a mean stress. So if the maximum is 50 and the minimum is 50, then the mean is 50, and we just have static loading. So under static loading, we know that we have some yield point, Sy, and we have some ultimate strength, SUT, right? That the part will begin to yield, and then at some point the part will fail. So we're kind of sticking ourselves in the ductile material range here. For brittle materials, you could just put those 2 points much closer together. All right. So if this part is going to yield, it will yield if the combinations of A and M are greater than the yield strength. So this is the yield line. So we'll yield if the combination of those stress values is anywhere greater than if the combinations of sigma A and sigma M are greater than the yield strength. Now, in order to get fatigue life, we need to be on this curve. So this is our fatigue life such that the number of cycles is greater than 10 to the 6 cycles. It's less than 10 to the 6 cycles if we are outside of that line. Maybe a better way to say that. So outside that line is 10 to the 6 cycles. So we have a couple interesting regions in here. Let's call this region 1. In this region, we say that the part has infinite fatigue life, and it does not yield. Above the endurance strength, but below the yield strength, let's call this section 2, it has finite life and does not yield. Let's call this section here section number 3. In 3, we calculate that it has infinite life, but in fact it will yield. So no, it doesn't have infinite life. So this is, if we are in this section number 3, this is why we always check for yielding. Because the way our equations are set up, it won't tell you that you're actually in section 3 and you'll yield before you get to that infinite fatigue life. All right, and then maybe for section 4, just means that it will break. It will yield and it will not last an infinite number of cycles. So 3 is also not a region that we want to be in. 3 and 4. All right, so the equation for this line here is how we define our fatigue factor of safety. So how close we are to this line tells us how close we are to not lasting a million cycles. And so we can come up with an equation for that line to define our factor of safety, how close we are to it, as the amplitude stress that we are under over the endurance strength plus the mean stress over the ultimate strength. And this is called the Goodman failure criteria. Now notice that this doesn't tell you whether it's going to yield or not. So you also need to check for yielding. Now we could have done the same approach as sigma A, sigma M here. I'll do a quick one here, sigma M, where we've got the ultimate strength and we've got the yield point. And experimentally, the results are actually more of a curved line here, an elliptical. And that's where we come up, that's where the ASME elliptic comes from. So 1 over the fatigue strength squared equals sigma A over SE squared. This is an elliptic equation, sigma M over SUT squared. This is the equation for the ASME elliptic. they're going to get you very similar results. And by and large, Goodman is more well known. Historically, it's been used longer, but either value is going to be fine for most situations that you're going to find yourself in. And then, of course, either way, we still need to check whether or not something's going to yield. So we check, is the yielding strength greater than the yielding stress it's under? Now, there are multiple ways we could get to this point, to this line. So we could have some vector here that gets us to that point. And that vector is called the load line R. And what we care about is really the slope of R. So the R load line is calculated as sigma A over sigma M. All right, so all of that assumed normal stress, but it could be that we are under shear stress. So if we are purely under torsion, or direct shear, but that's pretty rare. But if we're purely under torsion, then we can also use the torsion version of this. The fatigue factor of safety would be the amplitude shear stress over the shear endurance strength plus the mean shear stress over the ultimate strength, the shear ultimate strength, where we can define these things. The shear ultimate strength, SUS, is about 6. This is based on von Mises stress, by the way. Is about 0.67 times the ultimate strength and tension. The shear endurance strength is 0.58 times the endurance strength and tension, and the yield strength and shear is generally about 0.577 again of the yield strength in tension. So we can make sure it doesn't yield in shear by saying that the shear yield strength needs to be greater than our maximum stress that we're under, including, of course, the any stress concentration factors that are necessary. All right, so what does this whole process look like if we put it all together? First of all, we're going to need to know, this is a process for fatigue failure analysis. For this sort of fluctuating load. First of all, we have to find our material properties, so specifically the ultimate strength and the yield strength. Next, we need to compute our endurance strength, SE, and then modify to become our more realistic endurance strength with the Marin factors. We then can calculate any stress concentration factors. Recall Kf is related to 1 plus Q times Kt minus 1. And then we multiply our stresses by that factor. So we can find, we can do it one of two ways. We could either multiply Kf times the stress and then calculate it, or we can find the mean and amplitude stress and then multiply them by our factors. So Kf times sigma A and kf times sigma mean. From there, we can apply our Goodman equation, or the ASME elliptic if you prefer, as 1 over NF times this combined thing here. For consistency, I'll just call it sigma A. Sigma A over SE plus sigma M over SUT. Then if this fatigue factor of safety is less than 1, then step 6 here is going to be calculate the life, calculate n number of cycles. So recall when we did our finite life, the stress was fully reversed. So we don't have fully reversed stress here. We now have some component from sigma M as well as sigma A. And so what we actually need to do is come up with an equivalent fully reversed stress. And that equivalent fully reversed stress is sigma A over 1 minus sigma M over the ultimate strength. It's basically just converting the stress case around a little bit. Now, finally, step 6 here, or 7 possibly, if we don't have a step 6, if we have a step 6, is to check for yield. Because even if we found infinite life, we may in fact be above the yield point, and then we will not in fact have infinite life. It will just yield. All right, a few notes before we get into applying this to some examples. So if we have a situation where we've got some stress value over time and it's fluctuating down here such that sigma M is less than 0, what that means is on average this part is in compression. And that's even the case, if at the maximum is above 0, but anytime the mean is below 0, it means our part tends to be in compression. And if that's the case, then because it tends to be in compression, it tends to not allow cracks to grow. So if cracks are not growing due to sigma M being less than 0, we want to be safe, we want to get rid of it out of our fatigue equation. So anytime sigma M is less than or equal to 0, change this, the Goodman equation, from sigma A over SE, sigma M over SUT. Change this to just ignore the sigma M part. So then you just have 1 over NF equals sigma A over SE. And you'll notice this looks exactly like the fully reversed case, because in fact it is. So that means we're just considering the amplitude portion. That's how much it fluctuates about that, which is going to be what causes that crack to grow. So anytime you're working with a part that's primarily under compression, ignore the mean contribution to the fatigue failure equation. All right, in the next video, we're going to go over some examples going through the whole process. That'll about do it for this video. So until then.